What's going on, everybody? Mr. Diamond, and we're here to work out our examples of determining oxidation numbers. So, I got the examples that were from my notes. I ran out of space because I am the most prepared person to ever exist, ever in the entire world. But we're going to start with our first example, and we're just going to work our way through these examples up here and discuss how to find the oxidation number of each individual element involved. So we're going to start with SCSO3. And I feel like I've said this phrase a lot of times in this class, but this is another one of those situations where you have a set of rules and you're really just solving a logic puzzle. If you use kind of your logical deduction skills and you follow those sets of rules, you should be able to figure out what the answer to the question is. So we're going to start with SCSO3. We've got SC, and I'm going to write this kind of below it just so I can know for my own reference what all of them are whenever we solve for it. I've got SC, I've got S, and I've got O. SC does not meet any criteria of any of our rules. So this is kind of your first step, is to go through the list and try to find any of them that fall into certain categories of the rules. SC, it's in the D block. It's not in the first two columns. There's no weird rule about it always having a specific oxidation number, so we don't know it off the top of our heads. Sulfur, same situation. It doesn't meet any of our criteria. Oxygen, however, and if I click to make sure that I've got the correct number rule so I can actually say the numbers as we're going through here. Rule number 4 says that oxygen usually has an oxidation state of -2 unless it's peroxide or it's in the presence of fluorine. And there's no fluorine, and this is not peroxide, so our oxygen is going to have a charge, or not a charge, a oxidation number of -2. Now in this case, that also happens to be the charge of oxygen, but those are not related. Those are two separate pieces of information. They just coincidentally are the same in this problem. A lot of times that may be the case, a lot of other times it may not be. And then for an example of that, sulfur is not going to be. So our next step is going to be looking at this. We need to find, well, none of the other rules give us any hints immediately, but we know that scandium is a metal, and we know that SO3 is a nonmetal. You can look on the periodic table, and you can prove that to yourself. That means this is an ionic compound, which you don't have to write this, but this is kind of trying to show you the logical steps that you're going to go to prove your answers here. And that means that we've got SC over here, and we've got SO3 over here, and they don't have a charge. So our total charge of this is going to need to be 0. Well, SO3 is a polyatomic. SO3 is sulfite, and sulfite has a charge of 2-. So now we actually do have something. We know that this whole piece right here needs to have a total charge of 2-, and we also know that our oxygen has a charge of -2, or an oxidation number of -2. Because this has a charge of 2-, the oxidation number of SO3 needs to equal -2. And if we know that our O's, every one of our O's is a -2 charge, whatever our S oxidation number is, whatever the oxidation number of our S is going to be, must add to whatever our oxidation numbers of our O is to make an oxidation number of -2. We need to have these electrons need to have gone somewhere to make the total available electrons in this case, or extra electrons in this case, to be a -2. So using our math skills here, we get this as -6. We add 6 to both sides. Our sulfur in this case has an oxidation number of +4. Okay, now that is weird compared to the other stuff that we've been looking at, or any of our charges of sulfur we've ever had. Sulfur, based on its position on the table, has an expected charge of -2. But in the case of a sulfite polyatomic ion, sulfur will actually have to have given up some of its electrons to make the oxygens happy. So it will have actually given up 4 of its electrons. It will have a +4 charge. Okay, we're going to go ahead and put that with sulfur, +4. And now we also know that because this SO3 had a 2- as its charge, and it also had a 2- as its oxidation number, we need our charge to balance out, and we need our oxidation number here to also balance out with that 2 minus. And the only thing that could be there that would make it so if it combined with a -2 oxidation number to have a 0 total oxidation number would be if it was a +2. Now, there's a lot that just went into this problem. There's a lot of kind of steps along the way that if you don't remember a lot from general chemistry, they might be a little bit confusing. And that's okay. I understand that. But you're going to really just want to have to go back and look through that if you're lost on about all that stuff, or ask me questions in class so we can kind of discuss it together. The best piece of advice, though, is you're just want to do a bunch of examples of these. The more examples you do, the better off these are going to be for you. So there's our first example. Second example, we've got Na2SO4. So we've got Na, we've got S, and we've got O that we need to know the oxidation numbers of. First step, Na, always +1, because it's in the first column. That was rule number 5, I believe. Rule number 5 was that group 1A and group 2A always have +1 and +2 respectively. And just like last time, our oxygen has a -2. That's because of rule 4. Then we get to use the same logic that we used before. Sulfate is SO4 with a 2 minus charge. That means it must have an oxidation number of -2. 4 times our -2. So again, there's 4 oxygens here. So those oxygens are contributing a total of -8 to our oxidation number. Plus whatever our sulfur is contributing is going to give us our oxidation number of sulfate. Now, you might be thinking, well, this sulfur just showed up again. I just had it as +4 over there. I'm just going to pull it down to this question. The answer to if you can do that is no. You cannot assume because sulfur was +4 up here that sulfur is going to be +4 down here. And if you've looked at the problem I've set out, you already can tell that that's not the case. And that's because sulfur will behave differently in different situations. It's just like the whole idea that, you can have oxygen in a whole bunch of compounds, and in some of those compounds, like water, you have to have it to live, and some of those other compounds, like hydrogen peroxide, you will die if you drink it. And some of those other compounds are sugars that we burn in our body for energy, and some of those other compounds are explosives. There's a whole bunch of different ways that it will behave, and in this case, so we can't assume that we are going to just be keeping the same charge every single time we see it. Every individual case, we have to start as though we have no idea what the charge is and solve it just for that one specific compound. So in this case, we end up with sulfur needs to have a +6 charge in order to balance out all of this. And if you notice, the total adding up of all of these things should be 0. 1 times 2 is 2. +6 is 8. 4 times -2 is -8. That leaves us with a completely balanced and no charge for our answer. Okay. Next, we've got KNO2. KNO2. I'm going to put K. I'm going to put N. I'm going to put O. The only one of these are, we have 2 of these that we have information on based on our rules. K is always +1. O is always -2, just like we've been doing before. In this case, NO2 has a expected charge of -1, so its oxidation number is going to be -1. So that's going to be 2 times -2 plus whatever N is should add up to be -1. That means we're going to have to add 4 to each side, so nitrogen is going to be +3. And again, you'll notice that this is not the expected charge of nitrogen. Nitrogen, we expect to have a charge of -3 in order for it to work in a normal chemical reaction, but this is not the charge. This is the oxidation number. And in this specific setup of a chemical equation or of a chemical formula, nitrogen is actually going to be down 3 electrons. It's going to have lost 3 electrons. Okay, next we've got N2. It's a pretty easy one. I'm actually going to do it over here. We've got nitrogen, and there's no charge. They're both the same atom. That means it's going to have an oxidation number of 0. Anytime it's just a single element or it's a diatomic molecule like N2, that's going to be no oxidation number. It does not have any it has an oxidation number. It has 0. Its oxidation number is 0. That wording is a little bit bad. Okay, we'll do another kind of easy one. The last one we're going to do is going to be the toughest one, so I'm going to do this in a slightly different order. Let me make this gap here. So we've got SiF4. So we've got Si and F. In this case, this is a molecular substance, but we're going to actually be able to follow our rules of our ionic compounds to try to figure out what the charge is going to be, or not of our ionic compounds, but it's the same kind of idea as when we made our ionic compounds in general chemistry. Go back to the beginning. What I mean by this, you'll be able to see in a second. So there is no charge, which means the oxidation number is 0. Our oxidation number of fluorine is always -1, and there are 4 of them, so that means that fluorine is contributing a -4 to it. So silicone, normally we don't know what its charge could be. Its expected charge would be -4, but its oxidation number in this case is actually going to be +4, because when it's reacting with fluorine, fluorine is so good at stealing electrons, it is going to steal all 4 of silicone's electrons, and that's going to make it have an oxidation number of +4, or it's going to be as likely to. Again, this is a covalent compound, so really there's not even any stealing going on in here. It's just going to be connected to it. We're just saying that in every one of these cases, the fluorine is basically pulling the pairs of electrons as close to it as possible, so it's ready to rip them off if this breaks. It wants to be the one on each of those sides that ends up with an extra electron. And that means silicone is currently, if they were to divorce, if they were to separate, fluorine would be losing 4 electrons in the exchange. But they're not currently losing 4 electrons. It is currently set up in a way that it would lose 4 electrons if the bonds were to break. The last example is definitely the most complicated. We've got CrBrO43. So let me scoot this down a little. We've got Cr, we've got Br, and we've got O. O is not with hydrogen, so it's going to be a -2, or not with fluorine, so it's going to be a -2. Your next question gets a little bit weird. You might be inclined to say, well, there's bromine, and bromine is a halogen. But if you remember in the rules, I specifically said that we cannot just assume that bromine is going to behave like fluorine. Fluorine is way more reactive than anything else on the table, so it gets to have special rules we hold it to. We cannot assume that bromine is going to behave the same way. So then your next instinct is going to be, okay, well, this looks like a polyatomic, so let's figure out what polyatomic it is. And unfortunately, because I am a jerk, bromine with 4 oxygens attached to it is not on the polyatomic sheet that I gave you. And even more than that, bromine with any amount of oxygens is not on this list. So what you're actually going to have to do for this question is, well, a lot of you would probably Google it, but what I would rather you do is to think logically. Bromine is in the group of halogens. Do I have another halogen in this polyatomic ion set that I could use and it would kind of behave the same? And the only one that comes to mind here is chlorate. Chlorate is ClO3 with a -1 charge, and it has chlorine. So this is bromate, or bromine is our base here. We want it to have 4 oxygens, though. And based on our rules of modifying our polyatomics, if we want it to have 1 more oxygen, we could just call that per blank 8. This was chlor for chlorine, so this is actually going to be BrO4 is going to be per bromate, which is not a polyatomic that we have ever talked about in class, and I've never expected you to have memorized, but you're now in advanced chemistry, and so you can actually make the logical deductions and the logical leaps that result in you realizing that you do actually have enough information to solve it. If you know chlorate is a -1 charge, and chlorine and bromine are halogens, and they're in the same group, or their same family, and we talked about how being in the same family means they have similar traits, you can assume that BrO4 would behave the same as ClO4, meaning that it would have a 1- as its charge, meaning that we can say -1 as an oxidation number is equal to 4 times -2 plus whatever the Br has. In this case, we're going to have to add 8 to both sides, and we get that the Br is +7. Now, I've also done this in this order for another reason, Notice that you might be going, well, whoa, bromine is supposed to be a -1 and now it's a +7. Does that mean that we can just do the opposite? Like if it's oxygen, instead of being -2, it would be +6. If it's nitrogen, instead of being -3, would it be +5? And the answer to that question is no. And I specifically picked these examples before to show you that you don't have a guarantee of that. Nitrogen normally would have been a -3. We didn't make it a +5. Sulfur here normally would have been a -2. Yeah, it was a +6 here, but it was a +4 up here. So you cannot just assume that it's going to be the opposite. It's going to lose electrons instead of gain electrons. That does not work every time. Okay, we now know, since we've done our logical deduction skills, that BrO4 is a 1- charge. There are 3 of them. That means that Cr must have a 3+ charge, and that means that its charge must be +3, or its oxidation number must be +3 to counteract the oxidation number of perbromate. Okay, that was a very tricky last problem, but the rest of them are a lot more similar to what you would actually be doing for this class. If you have any questions, please send me an email. We're going to be practicing this in class, so you'll have plenty of time to go over any more questions that you have. In the meantime, though, this is Mr. Diamond signing off. Have a great rest of your day, everybody.